You already know how to multiply matrices, but there's far more going on than the standard recipe reveals. Here are two matrices A and B, and their product C equals A times B. We're going to explore 5 different perspectives on the same multiplication. First, a single entry, how one cell of the product is computed. Second, a full column, the column way. Third, a full row, the row way. Fourth, a rank 1 outer product where we think of columns of A times rows of B. And fifth, colored block partitions, the block way. One operation, 5 windows. Each one reveals something the others hide. Method 1, entry by entry dot products. This is the standard rule. Matrix A has size m by n. Matrix B has size m by p. Their product C has size m by p. The shared dimension n must match. A's column count must equal B's row count. Now, a dot product, also called an inner product, takes two vectors of equal length, multiplies corresponding entries, and sums the results into a single number. The entry Cij equals the dot product of row y of A with column j of B. In formula form, Cij equals the sum from k equals 1 to n of Aik times Bkj. So to compute any single entry in the product matrix, you slide out the corresponding row of A and the corresponding column of B, line them up side by side, multiply entry by entry, and add everything up. Let's walk through a concrete example. A is a 3 by 4 matrix, B is a 4 by 5 matrix. So the product C is 3 by 5. We want to find entry C34. Row 3 of A is 2, 0, 5, 1. Column 4 of B is 4, 3, 1, 7. Now we pair them up and multiply. 2 times 4 is 8. 0 times 3 is 0. 5 times 1 is 5. 1 times 7 is 7. Finally, we add them all together. 8 plus 0 plus 5 plus 7 equals 20. So C34 equals 20. In summation notation, C34 equals the sum from k equals 1 to 4 of A3k times BK4. That gives us one entry at a time. Now let's zoom out and compute an entire column at once. This is method 2, the column way. Take column J of B, multiply the full matrix A by that single column vector. The result is column J of C. But here's the key insight. Every column of C is a linear combination of the columns of A. What does that mean? A linear combination scales each vector in a set by a coefficient, then adds them all together. Specifically, column J of C equals B1j times column 1 of A plus B2j times column 2 of A plus B3j times column 3 of A plus B4j times column 4 of A. The coefficients come directly from the entries of column J of B. So each column of A gets scaled by the corresponding entry in that column of B, and then we add them all up. So this leads to a beautiful consequence. The column space of C lives inside the column space of A. Every column of C is built from columns of A, so C cannot reach outside the span of A's columns. The column way sliced C column by column. Now let's flip it. Method 3, the row way. Take row I of A, multiply that single row vector by the full matrix B. The result is row I of C. Every row of C is a linear combination of B's rows. The coefficients are the entries of row Y of A, AI1, AI2, AI3, AI4. Row I of C equals AI1 times row 1 of B plus AI2 times row 2 of B plus AI3 times row 3 of B plus AI4 times row 4 of B. And this immediately tells us something important. The row space of C lives inside the row space of B. Now notice the beautiful symmetry between these two methods. The column way combines A's columns using B's entries as weights. The row way combines B's rows using A's entries as weights. In the column way, the unit of output is a column of C. The driver is a column of B. It combines columns of A, and it reveals that the column space of C is contained in the column space of A. In the row way, the The unit of output is a row of C. The driver is a row of A. It combines rows of B, and it reveals that the row space of C is contained in the row space of B. Two sides of the same coin. We've sliced C into columns and rows. Now let's slice A and B differently. Take one column of A and one row of B and multiply them. This is called an outer product, a column vector, m by 1 times a row vector. 1 by p produces a full m by p matrix. Contrast this with the dot product, also called the inner product. A row times a column gives just one scalar, a single number, but the outer product gives an entire matrix. Let's see an example. Take the column vector 2, 3, 4 and multiply it by the row vector 1, 6. We multiply each entry of the column by each entry of the row. 2 times 1 is 2. 2 times 6 is 12. 3 times 1 is 3. 3 times 6 is 18. 4 times 1 is 4. 4 times 6 is 24. The result is the 3 by 2 matrix. 2, 12 in the first row, 3, 18 in the second row, 4, 24 in the third row. This is a rank 1 matrix. A rank 1 matrix has the simplest possible structure. Every column is a multiple of the vector 2, 3, 4, and every row is a multiple of the vector 1, 6. Now here's the big idea. The entire product A times B equals the sum of n rank 1 matrices. Column 1 of A times row 1 of B gives one rank 1 matrix. Column 2 of A times row 2 of B gives another rank 1 matrix. Continue this pattern through column n times row n. Add all n of these together, and you get the product C. In summation notation, a times B equals the sum from k equals 1 to n of column k of A times row k of B. Every matrix product decomposes into the simplest possible building blocks. Each term in this sum has rank 1. All of its column information lies along a single direction, and all of its row information lies along a single direction. And these rank 1 pieces stack and combine to form the full product. Numbers became vectors in methods 2 through 4. Now let's take it further. Replace vectors with entire submatrices. This is method 5, block multiplication. Partition matrix A into a 2 by 2 grid of blocks, A1, A2, A3, and A4. Partition B the same way, B1, B2, B3, and B4. We multiply using the same row times column pattern, but now with blocks in place of numbers. The top left block of C equals A1 times B1 plus A2 times B3. Let's work through an example. A1 is the matrix 1, 2, 3, 4. A2 is the matrix 5, 6, 7, 8. B1 is the 2 by 2 identity matrix with 1s on the diagonal and 0s elsewhere. B3 is the matrix 2, 0, 0, 2. First compute A, 1 times B1. That's the matrix 1, 2, 3, 4. Multiplied by the identity, which simply gives 1, 2, 3, 4. Next, compute A2 times B3, that's 5, 6, 7, 8 times 2, 0, 0, 2, which gives 10, 12, 14, 16. Now add the two results together. 1 plus 10 is 11, 2 plus 12 is 14, 3 plus 14 is 17, 4 plus 16 is 20. So the top left block of C is 11, 14, 17, 20. An important note, the blocks don't need to be equal sizes. They just need compatible dimensions at each subproduct. Block multiplication is what powers large-scale computation and parallel processing. Now let's see all 5 methods side by side. At the center, we have C equals A times B. One product, but 5 different ways to understand it. Method 1, the entryway. Cij equals the dot product of row I with column j. We compute one number at a time. Method 2, the column way. Column j of C equals A times column j of B. This tells us that the column space of C lives inside the column space of A. Method 3, the row way. Row y of C equals row y of A times B. This tells us that the row space of C lives inside the row space of B. Method 4, columns times rows. A times B equals the sum of rank 1 outer products, column K times row k summed over k. These are the simplest building blocks of any matrix product. And method 5, block multiplication. We apply the same row times column pattern, but now with submatrices replacing individual entries. It scales the idea to any size. 5 windows, 1 truth. These aren't 5 different operations. There are 5 windows into the same truth. The more windows you have, the more of the structure you see. Each perspective, entry-level dot products, column combinations, row combinations, rank 1 outer products, and block multiplication reveals a different facet of what matrix multiplication really means. 5 windows, 1 truth. Next up, what happens when A times B does not equal B times A?